Hello everyone. Today I'm going to present my project for MAT 201, Mathematical Analysis 1. My topic is the fundamental theorem of calculus. My name is Zhang Pan and my student ID is MAT 2409037. Today, this presentation will focus on the motivation, statement, and applications of this theorem. The fundamental theorem of calculus is one of the most important results in analysis, as it connects two central ideas, integration and differentiations. Okay. Here is the outline of my presentation. I will first introduce the background and introduction. Then, I will state the fundamental theorem of calculus. After that, I will explain its meaning, briefly discuss the idea of the proof, and finally illustrate the theorem using examples and applications. Okay, here is the background. I will begin with the background. The idea of integration originates from geometric problems involving area. A classic example is approximating the area of a circle. Since the exact formulas were not always available, mathematicians approximate curved regions using simple shapes, such as rectangles or triangles. Use these to approximate the area of a circle. As these approximations become finer, they lead to modern concepts such as Riemann sums and Darboux lower and upper bound sums. Using Riemann integrals, we obtain a rigorous definition of the area. However, computing integrals directly from the definition is often very impractical, right? At the same time, differentiation was developed separately as a tool to study rate of change. For example, st. The slope of this is the velocity. This naturally leads to the following key question. What's the relationship between these? Integration and differentiation. Okay, the fundamental theorem of calculus will provide you with a precise answer to this question. This is our topic. Okay, next one. This slide states the fundamental theorem of calculus. Okay, let's see. Let f be a bounded Riemann integral function. If x is continuous at a point x0, x0 belongs to the interval a to b. Define big fx equals to a to x integral fu du. Then, if fx is differentiable at x0, then we can get the derivative of big fx equals to small fx0. This is the fundamental theorem of calculus. The theorem tells us that big F is differentiable at x0 and its derivative is exactly small fx0. In other words, differentiation reverses integration as points where the function is continuous. This is the statement of the theorem. Okay, to better understand the theorem, we look at its meaning. The function big fx represents the accumulative area under the curve y equals to fx from a to x. Let's see. yx. Then the region here is the accumulated area. If the function f is continuous at x, then the rate at which the area changes is exactly the value of the function at that point. In other words, let it be called A. It is the accumulated integrate from a to x. This explains why integration and differentiation are inverse processes. Yeah. This is the meaning of the theorem. Okay, after knowing the statement of the theorem, I will now briefly explain the idea of the proof without going into technical details. The goal is to show that the derivative f at x0 exists and equals to small f x0. Yeah, this is what we want to show. We write the difference quotient as an integral over a small interval. Because small f is continuous at x0, its value near x stay close to x0. Because it is continuous, right? So, if f gets more close and close than to x0, fx equals to, right. This allows us to estimate the integral and show that the limit exists. Therefore, continuity plays a crucial role in the proof. This is the rigorous proof of the fundamental theorem of calculus. Okay, we know the fundamental theorem of calculus, then we need to use it. We need to learn how to apply it into our reality. Next, I will illustrate the theorem using an example. Here, we consider a piecewise defined function on 0 to 2, a bounded closed interval. Although the function is not continuous everywhere, we can look at here. When x equals to 1, get close to 1, negative, fx equals to negative 1. But when x close to 1 plus, it equals to 2. So fx they are not equal. So fx is not continuous at x equals to 1. Although the function is not continuous everywhere, it is piecewise continuous and therefore Riemann integrable. We define the accumulation function fx equals to integral from 0 to x fu du. This example helps us understand how continuity affects differentiability. Okay, from small fx we can get big fx. After computing the integral, we obtain the form of big fx when it equals to minus x when x in the interval from 0 to 1, and 2x minus 3 when x is between 1 and 2. Big fx, we can observe that at x equals to 1, fx minus 1, and when x it is minus 1 too, so they are equal. We can infer that fx is continuous on 0 to 2, including 1. However, f is differentiable only at points where the origin function small f is continuous. At x equals to 1, the function small f is not continuous, but the derivative does not exist. This example confirms the condition stated in the fundamental theorem of calculus. It's not continuous, so this does not exist. Okay, here is another example. Consider the function fu equals to sine mu square, which is continuous everywhere, yeah. Using the fundamental theorem of calculus, we can directly compute derivatives of integrals without evaluating the integral. It is continuous, so we can use fundamental theorem. Directly. This is especially useful because integrals like this one cannot be expressed using elementary function. So we can use the fundamental theorem to help us to do it. The theorem greatly simplifies these problems. Okay, let's make a conclusion. The fundamental theorem establishes a piecewise connection between integration and the differentiation. It shows that the derivative of an accumulation function recovers the original integrand at the point of continuity and plays a central role in mathematical analysis. Okay, thank you for your attention. And here is some references I used for this presentation, including standard calculus textbooks and lecture notes in our class. Okay, thank you. Thank you for listening.